lecture on geochronology. I'm going to try to make these in 15-minute increments, and then sometimes we'll just have to build when it's a longer story. Right? Last time we talked about the age of the Earth and what was an atom and then what was an isotope. We really didn't dive into much depth. There was a lot of background. So we were under, what number were we under? We were under isotopes, under Roman numeral 2, radioactivity. So let's keep going from that point. And one of the things I want to point out is that some of our isotopes are radioactive and some are stable. So let's just have something here. C, some isotopes are stable. There's a whole field of petrology based on stable isotopes, which we are going to skip altogether this semester. And instead, we're going to talk about the 51 different radioactive isotopes that lose energy. So radioactive isotopes. And when we say that they lose energy, the other way we talk about this is that they decay. So 51 radioactive isotopes decay. This means they lose energy. And they can lose energy in a couple of different forms. We're going to go through those right now. The first form is called an alpha decay. Alpha decay is when a helium atom is ejected from the nucleus. So think about what helium is. Helium has 2 protons and 2 neutrons. And so when you have helium decay, you actually drop your mass by 4 minus. And you put your charge, so let's say we change mass 4 minus. And we also change the charge, right, by 2 minus. And the way I'd want you to visualize what's going on when there's an alpha decay is that there's essentially a bowling ball that's smashing through a crystal lattice. We see evidence for this under the microscope. Maybe you've seen it this semester. Take a look at this picture. Oh, it's a little grainy. This is a photo from Alex Streckheisen. This guy has a great web page. I can even write his name down with a bunch of good photographs of thin sections. If it's something that you, well, let's not have that pop up. Instead, we go back to the pen. Okay, this guy's name is Alex Streckheisen, and he's got a bunch of great photomicrographs. But what we see are some biotite crystals, and in these biotite crystals, there are some zircons, and surrounding these zircons are these radiation damage halos. These are called pleochroic halos. Pleochroic halos. And they're evidence for the alpha particles being released from the uranium-lead decay inside zircon and blasting through the crystal lattice of the biotite, causing all this damage. That is one of the types of radioactive decay. The second type of radioactive decay to talk about is beta decay. Beta decay is not so much a bowling ball, it is just one electron that gets ejected. And so here, the mass stays the same, but charge, which direction does it go? It goes in a positive one direction, right? Because we're losing that electron. What you could think about that happens here is that a neutron turns into a proton. That could be something you could visualize for what the process is. And then there's this third type of radiation, which is actually the highest damage radiation. If we were to be exposed ourselves to radiation, it's called gamma radiation. And then this one, there's actually no particle, and instead it's just a high energy wave. This would be the most damaging type of radiation. And so all three of these are active as decay mechanisms within radioactive isotopes. Now, the next part we need to talk about here is how fast does this decay occur? And when we talk about the rate of decay, we usually use half-life as the phrase. So let's go rate of decay, and we think about this in terms of the phrase half-life. Sometimes the symbol for half-life is T to the 1/2. Right? That's a nice, good shorthand. And when we have this rate of decay, what we're doing is we're taking parent, so a little one here, we're taking parent, and this is some parent isotope that's radioactive unstable, and we turn it into a daughter isotope that may or may not be stable or radioactive. That's the mechanism that's going on. It's easiest to visualize this in the form of a graph. So let's try to draw a graph here. Here we have number of atoms on our y-axis, and we're going to have 100. We go to the middle here, there's 50. Here is 0 atoms. We're going to put our 25 and our 75 in. Down here we have half-lives. And so 0 half-lives, 1 half-life, 2, 3, and 4. And we're going to use this graph to show how you can have some radioactive decay and then also radioactive ingrowth. So the daughter ingrows and the parent decays. So let's say we start at time 0 with 100 atoms of parent. After 1 half-life, well, it's a half, right? So we go down to 50. After 2 half-lives, that 50 gets cut in half to 25. After 3 half-lives, it gets cut in half to 12 and a half, down to 6. And we could put in this decaying graph showing our radioactive decay. Now, what about ingrowth? I can get fancy here. I can change color, I think. And so if we start at time 0 with our daughter, after 1 half-life, we should have 50% ingrowth. After 2, we go to 75. Then, what is it, 87.5, 92. All right, and we have this function that's the opposite. And so this is our daughter ingrowth curve. The actual rate with which this occurs is different for all the different 51 schemes. In fact, the total range, there are some that are so fast, they happen on the order of milliseconds, and there's others that are so slow, they happen over billions of years. And so there's actually 55 orders of magnitude in nature that can be explored in terms of like how fast half-lives are. And what we're going to want to do as a geologist is we're going to recognize, is the process we're looking into fast or is it slow? And then we have to decide which half-life is appropriate for the problem we want to solve. So let's just put one little note here, is when we're trying to choose the system, so we'll just say choose system that is best to solve our problem. And that leads us to the master equation of geochronology. This is so important, it's going to need its own Roman numeral. And we're going to go back to black. And this heading is going to be called the master equation of geochronology. The master equation of geochronology allows us to actually use the half-life to solve for time. And the formula for this is D equals D naught plus N times e to the lambda t minus 1. Okay, great. But what do each of these things mean? Well, some of this is probably, you could have guessed it. D stands for daughter now. We need to measure how much daughter is present in the mineral today. D naught, this is how much daughter was present initially. Initially, that's what that says there. N, maybe we should have put P there, because N actually stands for the parent that's present now in the mineral. E is just the math function. Lambda is our decay constant. This is equivalent constant. This is equivalent to the half-life, okay? And it's known. This is like a law of physics. And then T we solve for. So a lot of times the equation solves. Okay, this is what we solve for. All right, so that is the master equation of geochronology. Any date you've ever heard about a rock, where this rock is 7.3 million years old, the geologists were using this equation to solve for it. And it actually introduces a couple problems to us, because how do we measure D today? How do we measure N today? D naught, that's even more tricky. So we're going to go B. To solve for time, what do we do? Dot, dot, dot. Well, we have to do a couple different things. We need to measure the D and N, the daughter and the parent, now in the mineral. And we do that using a mass spectrometer. Baylor has a mass spectrometer. Many different geology departments have mass spectrometers. This is how we count how much daughter and parent is present in a mineral. And then we also have to get this function, this decay constant. We get the decay constant from physicists. We look it up in a table. It's like one of the immutable laws of physics, is that this isotope decays at this rate. It's a known, okay? So we take the decay constant from physics. And that leaves us only with one last variable left, and it is D naught. And D naught is a problem. And we'll actually write that down as a problem. Because how can we know? How can we go back in time and figure out how much daughter was present initially? And what the solution ends up being most of the time is that we assume it is 0. And that means you can only make this assumption sometimes, and when you can, it's a very strong assumption. So let me give you an example. So zircon, should I make you tell me what the chemical formula is? Zircon has the ability to host lead. So if we were to break down zircon, here's the chemical formula for it. Zirconium is a 4+, and silicon is a 4+, but sometimes uranium, which is a 6+, can substitute in this lattice spot for zircon because the size is similar. Charge is a little different, but the size is exactly similar. So you can get uranium to substitute in for zirconium. And what will end up happening is uranium decays to lead, right? So lead is the daughter. Well, in the crystal of zircon, we can assume that lead D naught equals 0 because lead, which has this chemical formula, or this charge, it's 2+. But the atomic radius of lead is like super huge compared to that of zirconium or uranium. And so there's no way to get this huge bowling ball of lead inside the crystal lattice naturally. The only way to do it is by radioactive decay. And so for the example of uranium, lead decay, and zircon, we can make this assumption that D naught is 0. I think this is a good place to end Chapter 2 on geochronology. See you next time.